Mr. Clelland here for Clelland Maths. Today we're going to go through the whole of logarithmic and exponential functions at higher maths. This will cover the whole topic, including all the past paper questions and transformations of logs and exponential graphs. Before we get into that though, let's take a little word from our sponsor.
Clelland Maths is sponsored by Decay, the educational publisher for Scotland. They offer viewers of this channel a massive 30% discount. Just use the discount code ClellandMaths at leckyscotland.co.uk. The practice question books go all the way from level 3 to advanced higher and include national 3, 4 and 5 apps as well, so you can get any book you need for your studies. These are an excellent resource with questions on every topic and contain work solutions so you can see how the marks are awarded. As you go through the book, the questions get increasingly difficult, so by the time you finish the book, you'll be ready for your exams. Usually £9.99, just use the discount code ClellandMaths to get 30% off that. Link down below.
An exponential function is a function of the form f of x equals a to the x, where a and x are a member of R, which is the real numbers, and a is greater than 0. So it looks like this: f of x equals a, which we call the base, to the power of x, which we call the exponent. And we say that f of x is an exponential function to base a. Okay, so that's the basic idea of what an exponential function is. So some properties of exponential functions. Let's take, we've got f of x equals a to the power of x. When x equals 0, f of 0, plugging in 0 into this, gives you a to the power of 0, well anything to the power of 0 is 1. So when x is 0 for any exponential, we get 1 back on the y-axis. In other words, it always goes through 0, 1. Similarly, if I put 1 in, then f of 1 is just a to the power of 1, which is a, the base. So whatever this base is here, when x is 1, the graph goes through 1a. Okay, so let's just draw a graph to show you that. So here's what an exponential graph looks like. If I've got a positive 1, then I can go y and x. It says it goes through 0, 1, so along 0 up 1, let's just put 1 on the x-axis, y-axis, and it goes through 1a. So along 1 up a somewhere, and it just looks like this. It's like an exponential curve. As x gets bigger, it gets steeper and steeper and steeper and steeper. And it kind of approaches 0 on this side slowly, but it never actually reaches 0. Let's look at it when we get a negative value. So we've got y and x, and then we've gone through 1, and it goes through along 1 up a. So we would get a curve that looks like that, approaching 0 from that side. And that's when your a is negative. Okay, let's look at some examples of sketching exponential functions. Example 1, sketch the curve with equation y equals 6 to the power of x. So we need to work out where it cuts the axes. So when x equals 0, we get y equals 6 to the 0, which is always 1. So we've got 0, 1. It always goes through 0, 1 when it's an exponential, unless there's a transformation, plus or minus on the end. Then we'll work out one other point. To work out one other point, we'll just always do x equals 1. So y equals 6 to the power of 1, which is 6. So we get 1, 6. And we get always the same shape. So we draw y and x-axis, just a little curve sketch, x and y. Note the point 1 on the y-axis. And then along 1 up 6, we'll just call that there 1, 6. And it's a curve that goes like this. And we're done there. E is one of the most important constants in maths, and it's often called Euler's number. It's an irrational number, so it never ends. Can't be written as a fraction, and it's approximately 2.718, or it goes on forever. The natural exponential function, f of x equals e to the x, is called the natural exponential function. It's got a lot of properties. For instance, when you differentiate it, you get it back itself. It's got lots of neat things you can do with it. We're going to look at graph transformations. For any graph, we can reflect it up, down, left, right, scale it. We've done that before. And if you're needing help with graph transformations, look at the functions and graphs topic. But each transformation emphasizes a point on the graph, and we need to keep track of these. So the best way to do it is just to make some sort of table to keep track of how things are changing. The same rules for transforming exponential graphs have, as I've said, been studied in the functions and graphs unit. So look at that if you need help. But here is essentially all the rules you need. So very briefly, if we add or take away a number on the end, we move it up or down. So in other words, the y part changes by a. If we times by a or divide by a, we scale it. It gets bigger by a, so we times the y by a or divide y by a. If we put a minus in front, we flip it upside down on the x-axis. Now this is where it gets tricky. When we put it inside the brackets, x plus a, we move to the left. And if it's x minus a in brackets, we move to the right. That means it's affecting the x coordinate. If we get a here, then we're compressing it by a units, so we have the x-axis value for that. If we divide by a here, then we need to double it there. And if we want to reflect it over the y-axis, we put a minus x here. You're best to see this in examples. So example 1, transformations of exponential functions. Sketch y equals 1 plus 2 to the power of x. So our basic graph is y equals 2 to the x. So let's look at that first. So if I just draw a little table, we're going to do y to the equals 2 to the x here, and we're going to see what happens when it's y equals, well, 1 plus 2 to the x. So remember from our previous example, our basic points, you've always got 0, 1, and then you've always got 1, and then the base is 2, 2. Now we're looking at what happens when we add 1 to that. Well, if we add 1, the y part changes. 0 is not changing, but we're going to go to 2. And 1's not changing, but we're going to go to 3. So we get 0, 2, and 1, 3 is what we need to draw. We're going to get the same shape though, because there's not been any reflections. So we just draw y and x-axis, x and y, and we note that it's now 0, 2, and we note it's now 1, 3, 1, 3, and we draw basically the same curve. It's just a bit steeper than it was. It's just moved up by 1. So we're going to go like this. Now we could note that here is actually 1 now, because remember it never touches 0, so now it never touches 1 because it's moved up by 1. And we're done there. Example 2 for transformations of exponential functions in graphs. Sketch a graph of y equals 3 to the 2x. So let's look at our basic function, which is just going to be y equals 3 to the x, and then look at what happens when you times that by 2 there. So our first point, remember, is 0 and 1. And then our other point is 1, and then the base is 3. So what happens when we times the x by 2? So 0 is the x part. 2 times 0 is still 0. So 3 to the power of 0 is 1. So we still get 0, 1. No big deal. But this time, if we times it by 2 when x is 1, then we get 3 to the power of 2. 3 squared. So that becomes 1, 9. It's been scaled, so you get 1, 9. Same shape as always. X and y. We've got 0, 1. And we've got a long 1 up 9, so it's just a lot steeper. 1, 9 instead of 1, 3. The asymptote, where it cut, what will still never touch the x-axis, so it just goes up like this. And we're done there. Okay, so in the previous examples, we were given the exponential functions. However, sometimes we're given information about the function without knowing what it is. In this case, we use information to determine the equation. So in other words, there's going to be unknowns like an a or a b or something like that. Let's do an example where you're given a picture. Part of the graph of y equals a to the power of x plus b is shown. Find a and b. So we need to look at our points to see what they're giving us. The points they give us are 0, 2, and they give us 3, 9. So I'll just take a note of the points. Now remember, first number's an x and the second number's a y, so we can just sub in. So when x equals 0, we get a to the power of 0 plus b equals 2. Well, a to the power of 0 is 1. So 1 plus b equals 2. Solving that, b equals 1. We've got our b straight away. And now for the other point, we've got 3, 9. So when x equals 3, we get a to the power of 3 plus b equals y is 9. Well, that's a cubed, but b is 1, because we just worked it out, equals 9. 9 minus 1 is 8. A cubed equals 8. So something times itself equals a is 2. So a is 2. We've worked out our a and our b. Okay, let's move on to graphs of logarithmic functions this time. A logarithmic function is a function of the form f of x is log base a x, where a is greater than 0 and so is x. Now there's a relationship between exponentials and logs, and that is that if we've got y equals a to the power of x, we can rewrite it as log ay equals x. A simple example would be, let's say we had 10 squared equals 100. Well, we can rewrite that as a log, because we've got log now base 10 of 100 equals 2. And I always remember these two. And you can think about this. If I've got 10 in the base, 10 squared on the other side equals 100. Or conversely, when I've got 10 squared equals 100, the base becomes 10, the answer becomes here, and then 2, the power becomes over that side as the power. So let's evaluate some logarithmic expressions. Write 5 cubed equals 125 in logarithmic form. So I've got 5 cubed equals 125. So that means that we now have got log base 5 of 125, the right hand side, equals our power of 3. Just double check, because I remember it this way, 5 cubed equals 125. So I'm done there. Okay, we have to evaluate log base 4 of 16. So that means that log base 4 of 16 equals some number, let's say it's a. So rewriting that as an exponential, 4 to the power of a equals 16. That's how I remember it. 4 to the power of a equals 16. So 4 to the power of what is 16? 2. A equals 2. 4 squared is 16. Okay, let's look at some ones like this. Log a base a 1. What's log base a of 1? Well, that means we've got log base a 1 equals some number b. So that means that a to the power of b equals 1. Well, to get an answer of 1 when you do a power, that means that the power has to be 0. So that means b equals 0. So log base a of 1 equals 0. The log of any base of 1 is always 0. That's a big key point there. Okay, what about log base a of a? How could we work that out? Well, that means that if I make that equal to some number b, a to the power of b equals a. I need to get a back. So that means that if I think of this power as 1 here, b must be 1. So log base a of a log of itself, same base, is always 1. And that's another key point to know. Okay, some basic logarithmic equations. Example 1, solve log base 5x equals 3. So I just translate that into 5 cubed equals x. Well, that's it. 5 times 5 is 25 times 5 is 125. And we're done there. Log base x of 81 equals 2. That means that x squared equals 81. The square root of x, something squared is 81. So that means that x equals 9. The square root of 81 is 9. Now notice here we don't get a negative because logs are not defined for negatives, and a square root, so it's just 9. The log function is the inverse of the exponential function, so we can reflect the exponential graph in the line y equals x to get the inverse function. And that means that when we do our points, when x equals 1, we get log base a of 1 is 0, the points flip to 1, 0, instead of 0, 1 is what it was before when it was an exponential. And similarly, when it was an exponential, it was 1a, it goes to a1. Every logarithmic graph of the form log base ax passes through 1, 0, and a1. So let's have a look at some graphs. Let's look at log base 6 of x. So when x equals 1, we get y equals log base 6 of 1. Our log of 1 is always 0, so we get the point 1, 0. And then the other point we need to look at is the base, which is 6. So we look at 6, we get y equals log base 6 of 6, which is 1, so the point is 6, 1. And then get our curve sketch. Y and x kind of comes up from here, and it goes through 1, 0, which is 1 there, and along 6, up 1, let's just call that 6, 1, and it just kind of curves up like that, getting slower and slower as it goes. And it never touches the y-axis. We say that that's an asymptote. It never ever touches that y-axis. Just like the exponential, if we reflect that, never touches the x-axis, and it goes up like that. So you can see the line y equals x is a mirror line because they're inverses. So again, we can look at graph transformations for logarithmic graphs, and we can scale it, move it, up, down, left, right, and all sorts. So just the same rules as functions. So functions and graphs, check that out if you need to. But here's the rules again. We did it earlier in the video, but just there for you in case you need to look at them. But this is a topic where practice just makes perfect, okay? So let's just move straight in an example. So transformations of logarithmic functions. Example 1, with the sketch graph of y equals log base 5 of x minus 3. So again, I'll set my table up, and this time I'm going to look at y equals the basic function of log base 5 of x and look at those points, and then see what happens when it becomes x minus 3 here instead. So our basic points, remember, are always 1, 0, and then our base, which is 5, and that's 1. You can do a little bit of sum here. X minus 3 equals 1. So adding 3 to get 4. So we must get 4 for x to get back 0. And similarly, we want x minus 3 to be 5. So that gives me 8 here to get back 1. So we've got our basic logarithmic graph still. So we've got 4, 0. So along 4, 0. And we've got along 8, 1. Let's just call that 8, 1. So basically it's a shift to the right by 3 because this is stuck. This is basically f of x minus 3. So instead of it not touching the y-axis, it'll actually not touch number 3. So I'll put a 3 here just to show that, and then just draw my curve. And we're done there. Okay, transformation of logarithmic functions, example 2. Sketch a graph of y equals log base 5 2x plus 4. So I'm going to start looking at log base 5 of x to start with, looking at our points for that. So always 1, 0, and then it's going to be along 5, because the base is 5 up 1. So now looking at, we need to split this up into 2 bits. Y equals log base 5 of 2x is what we'll look at to start with, and then we'll add the 4. So log base 5 of 2x, then we'll add the 4. So let's just do it in pieces so we don't make a mistake. So 2x means that must be a half, because 2 halves is 1. And then we get 0 still. And then that must be 5 halves, because 2 times 5 halves is 5. I'm just dividing by 2 instead of timesing by 2. You see the opposites coming into here, and we get 1 still. And now we need to add 4. Now we're not adding 4 to x, we're adding 4 to y. So that becomes a half 4 up the y-axis, 5 halves, and 5. So we've got a bit of scaling going on here. But you'll still get the same sort of graph. So if I draw the y and x axis, first of all, I'll show you it by drawing it separately. So let's draw our normal log base 5x is this one. It goes along 1, 0, and then somewhere 5, 1. So then we can draw log base 5 2x if we have to. Well, all that's happened with that one is the points have changed. It's got a half 0, so that's a half, and we've got 5 halves 1, so we'll just take a note. 5 halves 2.5 and 1, but it's still basically the same graph. Nothing else has really changed. And then we've moved it up by 4 for the final part, so our final answer, although you can just jump straight into the final answer if you're happy with that, we've got a half 4, and we've got 2.55, and again it will still hug the y-axis, go something like that. And that is our final answer. Y equals log base 5 of 2x plus 4. And we're done there. Again, we can look at logarithmic equations with missing constants and look at graphs to see if we can work out those missing constants as we did in the exponential one. So let's get into that straight away with an example. Missing constants, example 1. The graph of y equals log base a of x is shown, find a. Well, 1, 0 is never going to help because it's always 1, 0. So I look at 5, 1. So looking at 5, 1, that means x and the y. So we've got y is 1 equals log base a of 5. So that means that a to the power of 1 equals 5. Or in other words, a is 5. And we're done there. Here's another example of missing constants. Y equals log base m of x plus k is shown. Find k and m. Well, we're given 2 points, so we might as well sub them in. So let's look at minus 4, 0. So we've got y equals 0 of log base m of minus 4 plus k. That means that translating that to an exponential, m to the power of 0 equals minus 4 plus k. But m to the power of 0, remember, is 1, is minus 4 plus k. So 5 equals k. Or you could have realised that it's moved along by 5 to the left, because it usually is at 1. If you want to think it like that, that's a nice way to do it as well. And then looking at our 5, 1, well, we've got y, which is 1, equals log base m of 5 plus k. Well, we now know k is also 5. So that means that m to the power of 1 equals 10. So m equals 10, and we're done there. The base is 10. Okay, let's start looking at some rules of logarithmic functions away from graphs. And just a quick reminder, a logarithmic function is a function of the form log base a of x, where a and x are greater than 0. And remember the relationship, if you've got y equals a to the power of x as an exponential, it can get transferred into a log by log base a of y equals x. A couple of rules also remember, log base a of 1 equals 0, and log base a of a, log of itself, is always 1. So log of 1 is always 0, log of itself is always 1. So let's have a look at some tasks. We have to use a calculator to write out the 3 decimal place the value of the following. So I'm going to do this for you just to get an idea of logs. So log base 10 of 10 is, well, 1. And let's get our calculator out. So log base 10 in a calculator, and my one is just called the log button, and yours probably is as well. So you just press log and 2, and it says 0.301. 10 of 5, don't get confused here, it's not 2. 10 to the power of something is 5. It is 0.699. Don't worry about my calculator doing something else in there, it's just the final answer we need. Log of 800 is 2.903. If I want log base 10 of root 10, I press log base 10, square root 10, and make sure I close my brackets, I suppose. And I get 0.5. I don't know if that is surprising to you, but it shouldn't be. 10 to the power of something is root 10. Well, the something must be the power of a half. 10 to the power of a half is the same as root 10. And then last one, log of 0.6 is minus 0.222. So that's how you use a calculator to work out a log as a number, okay? Now, this is the second task I wanted to look at. I want to look to see if there's a relationship between times in logs and adding logs. So we've got some numbers here, and we have to work out log 10ab, log 10a times log 10b, log 10a plus log 10b. Now you might not already know the answer because you've been taught it, but for the sake of this video, I'll show you anyway. So I've got log 10, 2 3s is 6. So let's look at log 6. We get 0.778. 4 7s is 28, so log 28 is 1.447. And 8 6s is 48, so that gives me 1.681. So now we want to do log base a times log base b. Well, that means I'm doing log 2 times log 3 0.144. In other words, not related to log a times b. Let's do it for all of them. 4 7s is 28, so log 4 times log 7, 0.509. Again, no relationship it would seem. Log 8 times log 6. So it basically proves 0.703 that log of AB does not equal log A times log B, but does it equal log A plus log B? Well, you probably already know the answer to this. So I've got to go log 2 plus log 3. Look, it's exactly the same, 0.778. And if you do it for all of them, you'll get the same answer, 1.447, and you'll get 1.681. In other words, there's a rule for logs. Log AB equals log A plus log B. Same base, so it has to be the same base. So it's an extension of the laws of exponents, because exponents and logs are related, and that's where it comes from. So check an example. Log 2 base 8 plus log base 2 of 4 would equal log base 2 of 8 times 4, which is 32. Now can we work that out? That means that 2 to the power of something, I'll just call it a, equals 32. 2 2s is 4, times 2 is 8, times 2 is 16, times 2 is 32, a equals 5. So log base 2 of 32 equals 5. A few checking examples, just making sure we're happy with that rule. We'll just leave our answer as a log if we have to, if we can't work it out. Log base 5, 3 plus log base 5, 6 is log base 5. 3 times 6 is 18. I can't find a power of 5 that makes 18, so I'll just stop. Log base 9, 3 plus log base 9, 27. So that's log base 9. 3 times 27, well that's 81. But I can work that out. 9 squared is 81, so that's 2. And we're done there. Now I'm not going to do the next one. It follows on. If log AB equals log A plus log B, log A over B is log A minus log B. So there's our rule there. If we're dividing A and B in a log, you can just take away 2 logs. So for instance, log base 2 of 8 minus log base 2 of 4 is just equal to log base 2 of 8 over 4. Well, that's log base 2 of 8 divided by 4 is 2. Log of itself is 1. So that gave me 1. A couple of other examples using that rule. So to combine log base 7 of 15 minus log base 7 of 3, so I can use the division rule. Log base 7, 15 over 3. Log base 7, 15 divided by 3 is 5. Second example, log base 4 of 6 minus log base 4 of 3, make sure the base is the same. Log base 4 of 6 over 3, that's log base 4 of 2. So that means 4 to the power of something, let's call it A, equals 2. Well, we could say A is a half then. Square root of 4 is 2. So it's a half. And we're done there. Another rules of logs that we can show quite similarly is that log base of anything of A to the power of B, I can just bring the B down to the front. It equals B log base X of A. So in other words, log base 2 of 2 cubed, since it's over power, I can take the power to the front and that just leaves 2, 2. But remember, log base itself is 1. So that's 3 times 1, which is 3. Let's have a look at some questions using that rule. Express 2 log base 7, 3 and log base 7x. So that means I'm just saying I've got a 2 at the front, so I can take the 3 and then make it squared. So that becomes log base 7 of 9. Simplify 2 log base 9, 3. Well, that's just log base 9 of 3 squared. That's log base 9 of 9, 1. Okay, so there's a note of all of our rules of logs. Log AB equals log A plus B. Log A over B is log A minus B. Log A to the power of B is B log A. And then remember, log of 1 is 0 and log of itself is 1. And we can combine these into much more tricky questions. So let's look at combining rules of logs. Example 1. Evaluate log base 1210 plus log base 12.6 minus log base 12.5. So rules of logs, I can add means times. So that's 10 times 6, which is 60, minus base 12 of 5. Minus means divide, 60 over 5. Log base 12 of 12, because 5 12s is 60, which gives me 1. And we're done there. Example 2. Log base 6 of 4 plus 2 log base 6 of 3. So I can't add yet because that 2's in the way. So I'll leave it there and move it up to a power, 3 squared. So that's log base 6 of 4, log base 6 of 9. And now add means times. Log base 6 of 4 and 9 is 36. So I'm looking for 6 to the power of something is 36. That's 2. 6 squared is 36. Okay, let's look at some further logarithmic equations. We previously did the ones which were basic, log base A of x equals 2 or something like that. Let's look at combining the rules of logs. So example 1, log base A 13 plus log base A x equals log base A 273. Looks quite complicated, but we can just combine the left. A, and we've got 13x, 1 log equals 1 log. Now, we've got a log on both sides here. If you've got a log on both sides and it's the same base and that's all you're left with, you can just eliminate the logs, just cancel each other out. So that means that 13x equals 273. And then we can just divide by 13. So that means that x equals, use a calculator if you want, 21. 13 21s is 273, and we're done there. So example 2, further logarithmic equations. Log base 11 of 4x plus 3 minus log base 11 of 2x minus 3 equals 1. And it tells you that x is greater than 3/2. So we can combine the left, because 11 is the same base, into 4x plus 3 over, because it's minus, 2x minus 3 equals 1. Now, so we can't just eliminate the logs here, because there's only a log on one side, but we can eliminate it, because that means, remember log base 10 of 100 equals 2, means 10 squared equals 100. That to the power of that equals 100. So that to the power of that equals all of this. So we can just say that 4x plus 3 over 2x minus 3 equals 11 to the power of 1. Times on both sides by 2x minus 3. 4x plus 3 is 11 bracket 2x minus 3. A little equation to solve. Expand the right hand side to get 22x minus 33. Move all the x's to the right, so 22 minus 4, that makes 18x. And move the minus 33 over, plus 33 plus 3 is plus 36. Dividing through by 18, x is 36 over 18, which is 2. And we're done there. Okay, for the logarithmic equations example 3, log base a of 2p plus 1 plus log base a of 3p minus 10 equals log base a of 11p, for p is greater than 4. Okay, let's solve this. Don't worry that it's a log base a or anything. Let's just see what happens when we combine it. It's all the same base. So we've got log base a, 2p plus 1, 3p minus 10, because add means times, equals log base a of 11p. So notice we've got a log of something equals a log of something, same base, so the logs eliminate. It doesn't matter if it's a base a, because you're never going to work it out anyway. So that means that 2p plus 1, 3p minus 10, equals 11p. Well, that's double brackets equals something, so I need to get that equal to 0, so I'm going to have to expand the brackets. So 2 times 3 is 6p squared, minus 20p, plus 3p, minus 10. You can use foil or a grid or anything else you want. Moving everything to the left, you get 6p squared, minus 20p, plus 3p, minus 11p, minus 10 is 0. So now I need to get it in p squared, p in number. So I've got minus 20, plus 3 is minus 17. Minus 17 minus 11 is minus 28p. Minus 10. Now luckily there's a common factor because 6 is a nasty number. Common factor is 2, I think. 3p squared minus 14p minus 5 equals 0. And then it's quadratic formula, or hopefully double brackets. So that gives me 2, double brackets, 0. So what we got? 3p and p. 3 5s is 15, minus 1 is 14. So it'll be there, will be it. And you've got 3p plus 1, and it'll be minus 5. Just double check. 3p squared minus 15p plus 1 is minus 14p. Minus 5, yep. So that means the first bracket equals 0, or the second bracket equals 0. So that means that p equals minus a third, or p equals 5. Initial conditions are important here. P is always bigger than 4, so that means that we can just eliminate that one, and therefore p equals 5, since p is greater than 4, and we're done there. Okay. Example 4 for the logarithmic equations. Solve log base 2 7 equals log base 2x plus a number 3. Okay, this looks more complicated than it actually is. This number 3 is going to bother a lot of people because I can't get rid of the logs or anything. But there's a trick, and the trick is this. Remember, log base of itself equals 1. So if I want to introduce a log here, I can just say 3 times 1 and just make it a special 1, log base 2 2. And I'll pick base 2 because everything else is base 2. And now I can combine the logs on the right. So it's a little trick that is worth knowing. Log base 2x plus log base 2 cubed. Combining the logs on the right hand side, we get log base 2 times, so it's 2 cubed is 8, 8x. Now the logs can just disappear. I've got a log of something equals a log of something, same base. So that means that 7 equals 8x. So x equals 7/8. And we're done there. Okay, remember we talked about e earlier on. Again, this is what e is. And you can write that as an equation, by the way, as 1 plus 1 over n to the power of n as n goes to infinity. And if you substitute very large values of n, you will get a value very close to e. So it's basically the limit as n goes to infinity. You don't really need to know that or work with that, but it's worth just seeing. But there is e there, 2.71. And we're going to look at exponentials and logs to base e. Now, log base ex is a bit clunky, and since we use base e all the time, we give it a special notation, ln, because it's called the natural logarithm of x. So we use ln x to mean log base e of x. Log base e of e would also equal 1. So in other words, ln e equals 1. Without a calculator, we have to write down the values of log base e of e squared. So that means that we've got 2 ln e, which is just 2. ln e, or log base e of e, is 1, remember. We've got 5 ln e, we've got 5. Root e, we're going to have to fix a little bit. So we've got ln for log base e. And then root e is e to the half. Well, that's just a half of ln e, which is just a half. It's the same as the one above. Ln cube root of e, well, that's ln e to the third, which is a third, because a third ln e, which is 1/3. And this one, that looks a little bit tricky, but we've got 1 over e to the third, which is e to the minus a third, which is minus a third ln e, which is minus a third. ln e 0 cannot be found. Easy way to explain why on this one is we're looking at ln 0. That means the same, remember, as log base e of 0. Well, let's say that's a. That means we're saying that e to the power of a equals 0. A number, which is 2 point something to the power of another number equals 0 is impossible. Another way to look at it is the graph. If you think of a graph, it always goes through 1 and then 1a. And it never touches the x-axis. In other words, it never, x equals 0 is undefined. So there you are. Okay, we have to use a calculator to work out log base e of 8 and solve ln x equals 9. Log base e of 8, we look for the ln button, press 8, 2.079. Very simple. Solve ln x equals 9. So you might like to think of that as log base e of x equals 9, and that means that e to the power of 9 equals x. So I want to do e to the power of 9 in my calculator. So to get e, I press shift and log on my calculator and put in the number 9. So x equals 8103.08, say, and we're done there. Okay, we have to simplify this, express an answer in the form a plus log base e b minus log base ec. So you need to be careful with this. Let's have a look at 4 log base e 2e minus 3 log base e to 3e. So we can put some powers in. Log base e 2e to the 4 minus log base e 3e cubed. Let's work out those powers then. So we've got log base e of 2 2s is 4 times 2 is 8 times 2 is 16 e to the 4 minus log base e of 27 e cubed. Now looking at the form that we want it in, we want a number plus log base e minus log base e of c. So I'm going to have to get a number somehow. So I'm just going to split this up into 2 logs. Log base e of 16 times e4, so plus log base e of e to the 4, and then do the same for the takeaway one. So I've got log base e of 27 plus log base e of e cubed. So that equals log base e of 16 plus, just think of the 4 coming down to the front, 4 log base e of e, well that's just 4, minus log base e of 27, and again, log base e of e with a power of 3 means the 3 can jump to the front, so it's just plus 3. And now we can get our numbers coming out. We've got 2 logs taken away. 4 minus 3 is 1, or to write it in the form we wanted, 1 plus log base E16 minus log base E27. Quite tricky that one to get it in the correct form. Solving exponential equations with unknown exponents, in other words with an x in the power position. Example 1 is solve e to the power of x equals 7. Now, the way you solve an exponential equation is you take the log of both sides, because you need to get rid of that power in the power position, because you can't think in terms of powers. So you take logs, and natural logs if it's base e. If it's any other base, like 10, you'll take log base 10. If it's 2, log base 2. But since it's natural logs, so we can just say ln e to the x equals ln 7 to keep it balanced. And then x comes to the front, we've got ln e equals ln 7. But remember, ln e is always 1. So that means that x equals ln 7. And we're done there. We could just work that out using a calculator. ln 7 is 1.946. And we're done there. Let's look at another few of solving equations with unknown exponents. So I've got a bunch here to try. E to the power of x is 10. So we say that ln e to the x equals ln 10. So that means that x ln e equals ln 10. So x is ln 10. And you can work that out to as many decimal places as you want using a calculator. ln 10 is 2.303. Okay, another one. E to the x is 1,000. So ln e to the x is ln 1,000. So x ln e equals ln 1,000. So finally x equals ln e is 1, remember. ln 1,000. Let's see what that is. 6.908. Another one, 2e to the x equals 0.3. So again, take the log of both sides. ln of 2e to the x equals ln of 0.3. So now we can split that up into two logs. Log base 2 plus log base x. So now we can split that up into two logs. So we're going to have ln 2 plus ln e to the x equals ln 0.3. ln 2 plus x ln e equals ln 0.3. So finally, remember this x ln e is just x. So we've got ln 2 plus x equals ln 0.3. So x is ln 0.3 minus ln 2. Now you can just use a calculator to work that out, or you can combine it, ln 0.3 over 2. Minus 1.897. Looking at D, we've got e to the x over 2 equals 5. This is D, sorry. So we can take the log of both sides. Take the power to the front then to get ln e out. So that means that x over 2 equals log 5. So x is 2 log 5, or log 5 squared if you prefer. Doesn't really matter if you're going to use a calculator. 2 log 5 is 3.219. Question E, e to the 2x equals 18. So log e to the 2x equals log 18. 2x comes in front to get log base e of log 18. So 2x equals log 18. So x is log 18 all divided by 2. Or a half of log 18, or 18 to the power of a half. But we'll just keep it like that, it's much simpler. Log 18 all divided by 2 is 1.445. And then the last one. e to the minus x over 2 equals 1. So log both sides. Take the minus x over 2 to the front. That gives me x over 2 where minus equals log of 1. Well, what's the log of 1? That's what you're asking yourself here. Log of 1 is 0, remember. Which means that x equals 0. And we're done there. Okay, some more solving equations with unknown exponents. Solve 7 to the power y equals 9. So this time we're not going to take the natural log. Take any base you want, actually. It doesn't make any difference whatsoever. So this time we've got 7 to the power y equals 9. So you can take the natural log or you can take log 10. Either of the two options, don't pick any other log because most of the time calculators will only do e or 10. I'll use 10 this time. Log base 10 of 7 to the y just to show you that it's fine. So the y comes to the front. And then we divide. So getting a calculator to work all of that out, log base 10, remember, log of 9 divided by, make sure you close that bracket, log of 7 is 1.129 to 3 decimal places. And we're done there. 5 to the 3x plus 1 equals 40. So let's do log base 10 of 5 to the 3x plus 1 is log base 10 of 40. So 3x plus 1 can come to the front to get log base 10 of 5 equals log base 10 of 40. So 3x plus 1 equals log base 10 of 40 over log base 10 of 5. Log 40 divided by log 5 is 2.292. So 3x plus 1 is 2.292. So 3x taken away 1 is 1.292. So finally, we get x equals, just divide, 1.292 divided by 3, 0.431. And we're done there. Okay, so looking at exponential growth and decay, we've previously that exponential functions are sometimes known as growth and decay functions because they exponentially grow or exponentially decay. And these model real life situations quite often. Think of accumulation or think of a virus spreading like COVID-19. That's exponential growth, okay? Or radioactive decay. So we can look at some equations of exponential growth and decay and solve some things. So imagine this one. Exponential growth and decay example 1. Example 1 says, mass g grams of a radioactive sample after a time t years is given by a formula, g equals 100 e to the minus 3t. What is the initial mass of a radioactive substance in the sample? And find the half-life. So initial mass is always initial t equals 0. So part A, when t equals 0, we get g equals 100 e to the minus 3 times 0. Which is equal to 100. 9 times out of 10 is always a number in front here. And now says, find the half-life of the radioactive substance. We know the initial mass is 100, so when it halves, the half-life, we need to half 100, so we become 50. So G is equal to 50. So we get 50 equals 100 e to the minus 3t. 50 over 100, there's that half coming out again, is e to the minus 3t. So we have to solve that equation. Now notice, we could have not known the initial, it could have just been like a. And because when you half it, you get a half a here, and when you divide it, you would get a half here. Essentially what I'm trying to say is if you don't know that number, whatever fraction it is goes here, a half or a percent. Okay, let's continue. 1/2 equals e to the minus 3t. So taking the log of both sides, log of a half, natural log, because base e is e to the minus 3t over log. So log a half equals minus 3t log e, but remember log e equals 1. So log a half equals minus 3t, and we're just about finished. T must be log a half over minus 3. Use a calculator for that bit. ln a half, 0.5, divided by minus 3, I'll put that in brackets actually, is 0.231. And what is our units on this one? Years. Doesn't ask us to change it to months or anything, so I'm done there. From Decay example 2, the world population in billions t years after 1950 is given by p equals 2.54 e to the 0.0178t. What was the world population in 1950? So in 1950, this is part A, so t equals 0, so p equals, it's going to be 2.54, but I'll show it exactly, 2.54 e to the 0.0178 times 0. So remember that's 2.54 times e to the 0, e to the 0 is 1, 2.54 billion. Make sure you answer that question. Write it in words if you want. Part B. Find to the nearest year the time taken for the world population to double. So if it doubles, we need to double the population. So that means that the population P is 2 times 2.54, which is 5.08. So we can say that our sum becomes 5.08 equals 2.54 e to the 0.0178t. But remember, we're going to divide by that here, which is going to give us a 2. So if we wanted to just go straight away, we could have said that 2 equals just this, and we would have got there quicker. So dividing by 2.54, we get 5.08 over 2.54 is e to the 0.0178t. That's 2. E to the 0.0178t. Log 2 then is log e 0.0178t. Taking the 0.0178t to the front, you get log e, which is 1, remember. So that means that log 2 equals 0.0178t. So t is log 2 over 0.0178 using a calculator. 38.941. And that's years. And then to answer the question, to the nearest year, 39 years is how long it takes for the population to double. And then you could probably say, well, that would be 1950, 60, 70, 89 is when it doubled, but we don't need to do that for now. Okay, let's look at experimental data on linear models. So the relationships of an experiment, and make sure there's an exponential relationship between the y and the x, or any other variables it is. So they can be difficult to interpret results because they're rapidly increasing or rapidly decreasing. Examples of these graphs would be like bacteria in a sample, rabbit populations, energy produced by earthquakes, and so on. But we can use logs to convert the exponential graphs to linear graphs by converting the axes to logarithmic scales. See that in an example, but if you do that, you get a straight line. Let's have a look. See, we've got polynomial equations of the form, let's say ax to the b. So let's say we've got y equals ax to the b. Now we're used to taking logs of both sides to solve these, so let's just do that. Log, let's say base 10 of y is log base 10 of ax to the b, right? Now we can use our rules of logs to separate that out. So log base 10 of y would equal log base 10 of a times xb, so plus log base 10 of x to the power of b. Now, that means we've got log base 10 of y equals log base 10 of a plus b log base 10 of x. Let me flip that on us. Log base 10 of y equals b log base 10 of x plus log base 10 of a. If I take away these logs for a minute here, that looks like y equals mx plus c. It's exactly what it is, except our axes are log base 10y and log base 10x. So we've got an equation y equals mx plus c. If we use a big Y equals mx plus a big C, then essentially our big Y equals log base 10y. Our M is just equal to B. And our C, our X is log base 10x. And our C is log base 10a. So if we're taking our original graph y equals ax to the b and drawing it normally, we would get an exponential curve. But if we had now instead changed the axes to log y, any log, but we'll use base 10 for this, and log x, we would get a straight line. And it's the C is where it cuts the y-axis, so that would be log base 10 of a, and the gradient would be some b. Okay, so that's what we're going to do when we do exponential data. We're going to do examples where we change the axes. Okay, here's an example. The results from an experiment are noted below, and it's told us log base 10x, these numbers, log base 10y, they numbers. The relationships between these data can be written in the form y equals ax to b. Find the values of a and b and state y in terms of x. Now, some teachers will teach you to memorize this stuff, but I prefer to stick with starting with y equals ax to the b and then coming up with it myself every single time. So I start with y equals ax to the b, and I take the log of both sides. Log base 10 of y is log base 10 of axb, and then just use my rules of logs. I did before, log base 10 of y equals log base 10 of a plus log base 10 of x to the b. Log base 10 of y is log base 10 of a plus b log base 10x. I want mx plus c, remember. So log base 10y equals b log base 10x plus log base 10a. And now I can see that's like a y equals an m, an x plus a c. So now I can use that knowledge. What about our gradient? Well, our gradient can be determined by any points because our data is given to us in terms of log x and log y. So our gradient is y2 minus y1 over x2 minus x1. So working out our gradient, let's just pick these two numbers and these two numbers. So 1.67 minus 1.33 for our y's, and 2.29 minus 1.7 for our x's. Now that simplifies to 0.34 over 0.59, which is 0.58 to 2 dp. So that means that since m is b, b equals 0.58. So we've already got log base 10 of y equals 0.58 log base 10 of x plus log base 10 of a. So let's sub in a point. We've got 1.33 and 1.7. So 1.70 equals 0.58 times 1.33 plus log base 10 of a. Now notice I'm subbing them straight in for here because it's quoted us in terms of log base 10x and a. So we can just work on that and solve it. 1.70 equals 0.986. Use a calculator plus log base 10a. Taking away the numbers, you get 0.344. So log base 10a equals 0.344. So 10 to the power is 0.344 equals a. Using a calculator, that gives me 2.208 to 3 decimal places, or 2.21 I suppose. So a equals 2.21. So now we have to write it in terms of y and x. So remember it was originally y equals a x to the b. So we've done it. Y equals 2.21 x to the power of 0.58. And we're done there. So the first time we did this, the x was down below and b was a power. We can also do this when x is a power, so a little bit different, ab to the power of x, but again, starting the same way. This time we take a log of both sides as usual. Using the rules of logs, you can get log base 10 of a plus log base 10 of b to the x take the x to the front. So there you are. There's our mx plus c. So putting that in that order, I'll write it as log base 10b and just put a bracket around it, x plus log base 10a, so you can really see that. So that is like y equals mx plus c. That's basically what it is, where y equals log base 10y, m equals log base 10b, well, x is just x. So since x is just x, c is log base 10a, what we're talking about here is a graph where the x-axis is still x, but the y-axis is logarithmic. So when x is in the power, that's what happens. And then it still cuts at some point on c at log base 10a. But again, I wouldn't worry about that because I would just do it like this every single time and you get there anyway. So let's look at an example like that. The results of an experiment are shown below, but this time it tells us it in terms of x and y, not log x and log y. And it says it can be formed in the relationship y equals ab to the x. Find the formula for y in terms of x. So y equals ab to the x, log, let's just pick base 10 of y, log base 10 of ab to the x. I would just start from there, I would not memorize things, okay? So log base 10 of y equals log base 10 of a plus log base 10 of b to the x, log base 10 of y, log base 10 of a plus x log base 10 of b. Rewriting that in the form y equals mx plus c, log base 10y equals, we want the x bit first, so log base 10b times x plus log base 10a. So that means we've got y equals mx plus c, and we're done there. So we've now got it in the correct form, so we need to make sure our axes are the same. So our y-axis is log 10y, and our x-axis is just the x-axis. So our original data is not given in that form, it's given in x and y, so I'm going to have to change it to x and log y. So that's quite easy. I just put x and log y. Log base 10, we'll say, of y. So our original x's were 1.30, 2.00, 2.30, and 2.80. So then we just put in, now we just check our y's, 7.69, 12.94, 16.12, and 23.10. So I'll do one, but you can do the rest yourself. The log of 7.69, so the first number is 0.885 or 0.89. Just do it to 2 decimal places because the rest are. I then do the next log of y, which is 1.11. The next log was 1.21, and the next one's 1.36. I'm getting these numbers just by taking the log base 10 of this, 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 and this, or y's, to make it the same scale. So now our gradient we can work out because we've now got the correct way. Our gradient is, let's say, y2 minus y1 over x2 minus x1. So you can work that out to get 0.22 over 0.7, which is 0.31 to 2 decimal places. But remember, our gradient is log 10b. So that means that log 10b equals 0.31. So 10 to the 0.31 equals b. Calculator for that. 2.04 to 2 decimal places. So there's a b. So we now need to work out our c. So we've got log 10y equals log 10 bx plus log 10a. So let's just pick another point. Let's just pick 1.3 and 0.89. So log 10y is 0.89 equals log 10b. Well, log 10b, remember, is 0.31. Don't need to work it out again. We'll know our b, but it's 0.31 times our x. So I picked 0.89, so it's 1.3 plus log 10a. And we just need to work that out. So 0.89 equals 0.40 plus log 10a. So log 10a equals 0.49. So that means that 10 to the power of 0.49 equals a, which is 3.09. We've got our a, we've got our b. Remember, y equals ab to the power of x. So y equals 3.09 times 2.04 to the power of x is our relationship, and we're done there. Now, you might have found that quite tricky. Sometimes the SQA leads you through this by showing you the graphs and showing you the axes as well. Have a look at the past paper questions. Past paper questions for all of this topic, logarithmic functions, exponential functions, are coming up now. Okay, evaluating numerical expressions. SQA Higher Maths 2015, paper 1, question 6. Evaluate log 612 plus a third of log 627. So I'll keep the log 612 to start with, but then I'll write that as plus of log 627 to the power of 1/3, because we can take that up. So that's log 612 plus 27 to the power of 1/3 is the cube root of 27, which is 3. So log 6(3). And then adding logs means we can just turn it into one log and the numbers times together. So that's log 6 of 12 times 3. That's log 636, which is equal to 2. And that's because, remember, 6 squared equals 36. So 2 is our final answer, and we're done there. Evaluating numerical expressions for logs, SQA Higher Maths 2016, paper 1, question 14. Part A, evaluate log 525, 2. Because remember, that means 5 squared equals 25. It's as simple as that. Part B, hence solve log 4x plus log 4x minus 6 equals log 525. So looking at our left-hand side, we combine that into one log by saying that it's x times x minus 6. So I'll do that to start with. Log 4x bracket x minus 6. And the right-hand side, log 525, well, we know that's 2, so we can just write 2. So then we can use our rules of logs to say that it's the base to the power of 2 equals the left-hand side. So in other words, 4 squared equals x times x minus 6 to eliminate the log. Now we're just going to get a quadratic. 16 equals x squared minus 6x. Moving over to the same side, you get x squared minus 6x minus 16 equals 0. So you've got a quadratic to solve. Hopefully that's factorizable. X and x, 8 and 2. Minus 8 plus 2, because minus 8 plus 2 is minus 6. Minus 8 times 2 is minus 16. So that gives me x equal to minus 2 or x equal to 8. But x equal to minus 2 is not a valid answer because the log of 0 or anything negative is undefined. So x has to be greater than 6. So we can just score that out and say that x has to be greater than 6 is the answer. So our final answer is x equal to 8. And we're done there. Okay, evaluating numerical expressions, SQA Higher Maths 2018, paper 1, question 6. Find the value of log 5250 minus a third of log 58. So we're going to combine these. So we'll keep the log 5250 hanging out for a minute. But we can say minus log 8 to the power of a third, because you can take coefficients up as a power. We'll work out that 8 to the power of a third then. So that's log 5250 minus, remember, to the power of a third is the cube root, so it's log 52. And now we can combine a minus, because a minus means you can do this number divided by this number. So as 1 log, we get log 5, 250 over 2. That's log 5, 125. So 5 squared is 25, so 5 cubed is 125, so the answer is 3, because 5 cubed is 125. And we're done there. Okay, evaluating numerical expressions, SQA Higher Maths 2019, paper 1, question 14. Part A, evaluate log 10 4 plus 2 log 10 5. So we've got log 10 4 plus log 10 5 squared, because I can take the 2 up. So that's log 10 4 plus log 10 25. And then we can combine that because we can times the numbers together. So it's log 10 4 times 25, which is log 10 100. Log 10 100 is equal to 2 because 10 squared equals 100. And there we are. Part B. Solve log 2 7x minus 2 minus log 2 3 equals 5. So we'll combine that into one log straight away by writing log 2 7x minus 2 all over 3, because a minus means we can divide. And that equals 5. So when using our rules of logs to eliminate, we've got a log on one side and a number. So 2 to the power of 5 equals this. So I can write that 2 to the power of 5 is 7x minus 2 over 3. So we need to work out 2 to the power of 5. Well, 2 twos is 4 times 2 is 8. Times 2 is 16. Times 2 is 32. So we get 32. So 32 equals 7x minus 2 over 3. So we can times 32 by 3. 32 times 3 is 96. So 96 is 7x minus 2. Add 2 to both sides. So 98 is equal to 7x. Dividing through by 7 then, you get 14 equals x, or nicer, x equals 14. And we're done there.
SQA Higher Maths 2022, paper 1, question 2. Evaluate 2 log 3x minus log 3 4. So it's just a 3-mark question, this one. The first one we're going to apply is the idea that 2 log 3 6 can be simplified to log 3 6 squared. So you get your first mark for simplifying this first log to log base 3 of 6 squared. And we can still write minus log base 3 of 4. As long as you wrote this, there's your first mark there. And then our second mark for combining the takeaways into one log as a divide. In other words, log base 3 of 6 squared over 4. There's our second mark there. Let's just take a note of that. And of course our third mark for then evaluating what that is, so working it out. So let's do some work on that. Log base 3 36 over 4 equals log base 3 of 9. Well, 3 squared is 9, so log base 3 of 9 equals 2. And there is our final mark right at the end for getting 2. Just a little note on this. If you did the correct answer but did no working on this question, you would get no marks. You have to show your steps to show that you understood it, otherwise the SQA just thinks you were guessing on this question. SQA Higher Maths 2023, paper 1, question 7. Part A, evaluate log 2 5 plus log 2 1 over 40. So part A, rules the logs again. Same base with a plus means I can times these two together. So that becomes log 2 5 times 1 over 40. So that is log base 2 of 5/40, which is log base 2 of an eighth, because you can divide by 5. Imagine it as 2 to the power of something as an eighth. Well, 2 to the power of 3 is 8, so 2 to the power minus 3 is an eighth, because it's 1 over 2 to the power of 3. So that means that 2 to the power minus 3 equals an eighth. So this means that the answer is minus 3. Part B. Given a is a member of the real numbers and that log 8a is negative, state the possible values of a. So we're saying that log base 8 of a is negative. So less than 0. We don't need to write the as. So log base 8 of a is less than 0. Let's just think about it logically for a minute. Let's imagine that we did 8 to the power 0. We would get 1. If we take a negative number then, we get 8 to the power of, let's say, negative 2. That's the same as 1 over 8 squared, which is a fraction. And if I take any negative number, 8 to the power of a massive negative number would be a fraction. So it's always going to be either as big as 1 or as small as almost 0. So that means that 0 is less than a is less than 1. We can see this on a graph, I suppose. If I draw a basic log graph, there is 1 there, and below the x-axis is when it's negative. So less than 1 is negative, but only up to 0. It never touches 0, so it's between 0 and 1. So that's another way you could have thought of it.
Evaluating numerical expressions for logs, SQA Higher Maths 2016, paper 1, question 14. Part A, evaluate log 5, 25, 2. Because remember that means 5 squared equals 25. It's as simple as that. Part B, hence solve log 4x plus log 4x minus 6 equals log 525. So looking at our left-hand side, we combine that into one log by saying that it's x times x minus 6. So I'll do that to start with. Log 4x bracket x minus 6. And the right-hand side, log 525, well, we know that's 2, so we can just write 2. So then we can use our rules of logs to say that it's the base to the power of 2 equals the left-hand side. So in other words, 4 squared equals x times x minus 6 to eliminate the log. Now we're just going to get a quadratic. 16 equals x squared minus 6x. Moving over to the same side, you get x squared minus 6x minus 16 equals 0. So you've got a quadratic to solve. Hopefully that's factorizable. X and x, 8 and 2. Minus 8 plus 2, because minus 8 plus 2 is minus 6. Minus 8 times 2 is minus 16. So that gives me x equal to minus 2 or x equal to 8. But x equal to minus 2 is not a valid answer because the log of 0 or anything negative is undefined. So x has to be greater than 6. So we can just score that out and say that x has to be greater than 6 is the answer. So our final answer is x equal to 8. And we're done there. Solving logarithmic equations, SQA Higher Maths 2017, paper 1, question 12. Given log a 36 minus log a 4 equals a half, find the value of a. So these are rules of logs to combine the logs. So that can give me log base a, and we've got 36 divided by 4, because of a minus, equals 1/2. So log base a, 36 divided by 4 is 9, equals a half. So eliminating the log, a to the power of a half equals 9. A to the half equals 9. So that means the square root of a, we could write that, I suppose, equals 9. So if I square both sides, a equals 81. And we're done there. Solving logarithmic equations, SQA Higher Maths 2018, paper 1, question 11. Diagram shows log 3x. On the diagram in the answer book, sketch the curve with equation 1 minus log 3x, and then find the point of intersection between the curves, which will be solved with logarithmic equations. So 1 minus log 3x, the minus part here tells me to reflect in the x-axis, and then the 1 part, which I'll do in another colour here, tells me to then move up by 1. So first of all, reflecting on the x-axis, this point will stay where it is, but this point will jump down here, and that would be at the moment as in point 3 minus 1. But now I have to move up by 1, so this point is going to jump up by 1, so that becomes 1, 1. And you can see this point goes up to 3, 0. So I can just write the number 3 here. Getting rid of my intermediate working, which you could use a rubber if you were doing this by hand. And since it's reflected, it's going to go down and through here. So we can just draw that in, down here, through the way, and there we go. It's a reflection in the x-axis. Okay, part B, determine the exact value of the point of intersection, simultaneous equations. So for part B, we've got y equals log 3x, but we've also got y equals 1 minus log 3x. So we can say that they are equal to each other and find x. So log 3x equals 1 minus log 3x. So taking the log 3x to the other side, you'll have log 3x plus log 3x. So 2 of them, 2 log 3x equals 1. I can take the 2 up as a power, so I get log 3x squared equals 1. Now I've got it in the form log of something equals a number, so 3 to the power of 1 equals x squared. 3 to the power of 1 equals x squared, and therefore I can find x. X equals 3 to the power of a half, or x equals the square root of 3. And we're done there. Notice it'll only be the positive part of this instead of the negative part, because if x was negative, then you would have log of a negative number, which doesn't exist, so it's just a positive. I can take a note of that. Just positive value, as x has to be greater than 0. Okay, evaluating numerical expressions, SQA Higher Maths 2019, paper 1, question 14. Part A, evaluate log 10 4 plus 2 log 10 5. So we've got log 10 4 plus log 10 5 squared, because I can take the 2 up. So that's log 10 4 plus log 10 25. And then we can combine that because we can times the numbers together. So it's log 10 4 times 25, which is log 10 100. Log 10 100 is equal to 2 because 10 squared equals 100. And there we are. Part B. Solve log 2 7x minus 2 minus log 2 3 equals 5. So we'll combine that into one log straight away by writing log 2 7x minus 2 all over 3, because a minus means we can divide. And that equals 5. So then using our rules of logs to eliminate, we've got a log on one side and a number. So 2 to the power of 5 equals this. So I can write that 2 to the power of 5 is 7x minus 2 over 3. So we need to work out 2 to the power of 5, or 2 2s is 4 times 2 is 8, times 2 is 16, times 2 is 32. So we get 32. So 32 equals 7x minus 2 over 3. So we can times 32 by 3. 32 times 3 is 96. So 96 is 7x minus 2. Add 2 to both sides, so 98 is equal to 7x. Dividing through by 7 then, you get 14 equals x, or nicer, x equals 14. And we're done there. SQA Higher Maths 2022, paper 1, question 8. Solve log base 6x plus log base 6x plus 5 equals 2, where x is greater than 0. There's a couple of different methods you could have used here, so I'll go through the alternatives for you. Let's call this one method 1. And the first method is to combine the two logs. The plus is one single log. So we could write that as log base 6 of x times x plus 5 equals 2. And there's your first mark there. Okay, moving to the second mark, we can write that as 6 squared equals x times x plus 5, or x times x plus 5 equals 6. So there's our second mark there. And then we can move on to try and solve that as a quadratic equation. So standard quadratic way, multiply out the brackets, we get x squared plus 5x, and that equals 36. So tidying that up, minus 36 equals 0. There's our third mark there for putting it in the proper quadratic form. And then our fourth mark, try to solve that. Double brackets, x and x. 9 and 4 times together to make 36, but take away make 5. So we've got plus 9 minus 4. So x equals 4 or x equals minus 9. But x has to be greater than 0 because it says so in the question. So we disregard one of the answers. So since x is greater than 0, x equals 4 is the only valid answer. And there is our final mark right there. We have to have stated that x equals 4. We disregarded the minus 9 to get that final mark. Let's look at method 2. So method 2 starts the same way. We apply the same rule as before. So we write log base 6 of x bracket x plus 5 equals 2. And we get our first mark. The log base 6 of x plus 5 equals the log base 6 of 6 squared. Because remember, log base 6 of 6 is 1, so that is 2. And that would give us our second mark. And then we can cancel the logs from both sides to just write x plus 5 equals 6 squared, or x squared plus 5x equals 36. And it continues in the same way as the last method. Minus 36 is 0. There's our other mark. And then for our final mark, solving that equation, we get x and x, 9 and 4, plus 9 minus 4 equals 0. So x equals 4 or x equals minus 9. But since x is greater than 0, x equals 4 is the answer. And there's our final mark there for 4 marks.
SQA Higher Maths 2023, Paper 1, Question 3. Solve log 5x plus minus log 5(3) equals 2. So, rules of logs, if it's a minus with the same base, you can divide these together. So, in one step, we get log base 5 of x over 3 equals 2. And then you need to get rid of the log. So, remember, it's base to the power of this equals this. So, in other words, 5 squared equals x over 3, or to write it nicely, x over 3 equals 25, 5 squared. X divided by 3 equals 25, so that means that x must be 3 times 25, so x equals 75, and we're done there.
SQA Higher Maths 2024, Paper 1, Question 9. Express log A5 plus log A80 minus 2 log A10 in the form log AK, where k is a positive number or integer. So rules of logs, log base A of 5 and 80 is plus, so 5 times 80, and then I'm dividing by something. Well, let's take that up to the top here. So let's do this one. That's log base A of 10 squared. So divide by 10 squared. So that gives me log base A, 5 eighths is 40, so that's 400. 10 tens is 100. That's log base A of 4. I have to leave it in that form, so we're done there. On exponential equations, SQA Higher Maths 2016, Paper 2, Question 6, otherwise known as experimental data with exponentials. Scientists studying the growth of a bacteria strain. The number of bacteria given is B equals 200 e to the 107t. State the number of bacteria present at the start of the study. The start means t is 0. You can either remember then that gives you e to the nothing, which is 1, so you get 200, or you can write that out actually. So at the start, t equals 0, so b of t equals 200 e to the 0.107 times 0. That's 200 times e to the 0, which is just 200. Calculate the time taken for the bacteria to double for part B. So if it doubles, that means that b of t becomes 400. So I can then write 400 as our b equals 200 e to the 0.107t was our equation, and we need to solve that. So divide by 200, 400 divided by 200 is 2, which is what you should get, e to the 0.107t. Now we can take the log of both sides, the natural log, so log 2 or log e2 equals log of e to the 0.107t, or if you prefer log e. Taking it down as a power, so you get log 2 equals 0.107t times log e of e, which is just 1. So log 2 equals 0.107t. Divide through by 0.107, t equals log 2, divided by 0.107. Get your calculator out and you will get about 6.48. So 6.48 hours, because hours was our unit of time. Solving exponential equations. SQA Higher Maths 2018, Paper 2, Question 11. A supermarket has been investigating how long customers have to wait at the checkout. During any half-hour period, the percentage of customers who wait less than t minutes can be modelled by this equation. P equals 100 times 1 minus e to the kt. Part A. If 50% wait less than 3 minutes, determine k. So I've got two values that I can just substitute in. So for part A, P equals 100, 1 minus e to the kt. So 50 is our percentage, equals 100 times 1 minus e to the power of 3k, because t is 3. Multiplying the bracket out, we get 100 minus 100 e to the 3k. So we can take the 100 over. 50 minus 100 is minus 50, equals minus 100 e to the minus 3k. Dividing through by minus 100, minus 50 over minus 100 equals e to the 3k. Well, that's a half, so that's 0.5 equals e to the 3k. You could have actually divided by 100 at this point here to get the half, worked it from there, but you get the same answer. Take the log of both sides. Natural log of 0.5 equals the natural log of e to the 3k. So the natural log of 0.5 equals 3k times the natural log of e. So that means that log of 0.5 equals 3k. So k is the log of 0.5 over 3. And we can work that out as a value in our calculator. You get minus 0.231. And we're done there. Part B says calculate the percentage of customers who wait 5 minutes or longer. So t is just 5. P is 100. 1 minus e to the minus 0.231 t, because k is minus 0.231. So when t is 5 minutes, p equals 100 times 1 minus e to the minus 0.231 times 5. And then we just need to work that out. If you do that in a calculator, you'll get 68.5. So it's 68.5%. Wait for less than 5 minutes. Because remember, this formula is for the number of percentage of customers that wait for less than a specific time. So that means that for those who wait 5 minutes or longer, which is what the question is, I just do 100 minus 68.5, which is 31.5%. Wait for 5 minutes or more. And we're done there. Solving exponential equations, SQA Higher Maths 2019, Paper 2, Question 9. Electricity on a spacecraft can be produced by a type of nuclear reactor. The electrical power produced by a generator is PT equals 120e to the minus 0.0079t. Don't be put off by this t, it's just part of a symbol to tell you that p is a function of time. Where PT is the electrical power in watts after t years. Determine the electrical power, keyword, initially produced by the generator. So if it's initially produced by the generator, that means part A, when t equals 0, PT equals 120 e to the minus 0.0079 times 0. Well, that gives you P of t equals 120 e to the power of 0, which is 120, because e to the power of 0 is 1. So we're done there. We could put the units in just to be clear. Watts. Part B, calculate how long it takes for the electrical power produced by the generator to reduce by 15%. So let's reduce this by 15%, by doing a little bit of maths. If it's reduced by 15%, there's 85% less. So that means that the power is going to be 0.85 times 120. And you just get a calculator out for that to get 102. So that's our new power. So that means that 102 equals the initial power, 120, e to the minus 0.0079 t. And we're going to solve for t. So it's an exponential equation, so I can divide through by 120 to get 102 over 120 equals e to the minus 0.0079 t. That gives me 0.85 on this side. E to the minus 0.0079 t. And if we're working in percentages, you'll realise that this number here will be basically what the question's asked us anyway, but I always start from here just to be on the safe side. So then we can log both sides using the natural log. The natural log of 0.85, or log e of 0.85, equals the natural log of e to the minus 0.0079 t. Pretty standard stuff. That means that log 0.85 equals, take the power down, minus 0.0079 t times the log of e. But the natural log of e is 1, so that means that log 0.85 is just equal to minus 0.0079 t, and therefore t is the natural log of 0.85 divided by minus 0.0079. And we can just get our calculator out and place log 85 over 0.0079, with a minus in front of course, and you'll get 20.6. And the units were years.
Question 10. The heptathlon was an athletics contest made of 7 events. Athletes score points for each event. In the 200 metres event, points are calculated using this formula, where P is the number of points and T is the athlete's time in seconds. Calculate how many points are awarded for a time of 24.55 seconds in the 200 metres event. So we just need to substitute 24.55 in for T. So we've got P equals 4.99087, 42.5 minus 24.55 to the power of 181. That's 4.99087 times 17.95 to the power of 1.81. 929.0368. Let's just make that 929.04. It doesn't quite specify whether the points are whole numbers or not, so that seems reasonable given the accuracy of the rest of the question. Right, in the part B, in the long jump event, points are calculated using this formula, where P is the points, D is the distance in centimetres, and K is a constant. It says 850 points are awarded for a jump of 600, calculate K, so we'll just substitute in and work from there. So we've got P, which is 850, equals 0.188807. D is 600, minus 210 to the power of K. So 850 equals 0.188807, 390 to the K. So dividing through, we get 850 over 0.188807 equals 390 to the power of K. Logging both sides, I'll just use the natural log. Taking the K to the front then. Equals
log of 850 over 0.188807 divided by the log of 390. So it's time to get a calculator to work these out. 1.40999, so k equals 1.41. SQA Higher Maths 2023 Paper 2 Question 13. A patient is given a dose of medicine. The concentration of medicine in the patient's blood is modelled by C of t equals 11 e to the minus 0.0053 t, where t is the time in minutes after the dose, c is the concentration in milligrams per litres. Calculate the concentration 30 minutes after the dose was given. Okay, so for part A, all we're doing is saying that c equals 11 e to the minus 0.0053, and that's going to be times on the top by 30. 11 times e to the power of, use my brackets, minus 0.0053 times 30, close my brackets, press equals. You get an answer of 9.3829, so 9.38 will be fine. Milligrams per litres, whether or not we'll take a mark off or not for losing the units. You need to get units if you can. Okay. Part B, calculate the time taken for this dose to become ineffective. And it says that the dose becomes ineffective when the concentration force is 0.66. So all we're doing is subbing in 0.66 to here and solving the resultant equation. So for part B, I'm going to write 0.66 equals 11 e to the minus 0.0053 t. So I can divide through by 11 straight away. If I do 0.66 divided by 11, I get 0.06 equals e to the minus 0.0053 t. Take the natural log of both sides. You can either write it as log e or ln. I'm just going to write ln. 0.06 equals ln e to the minus 0.0053 t. So ln 0.06 equals minus 0.0053 t, taking that to the front, ln e. But ln e is 1, or log e is 1. So that means that ln 0.06 equals minus 0.0053 t. And then dividing through by the negative there, I get ln 0.06 divided by minus 0.0053. So just calculator, ln 0.06 divided by minus 0.0053, and we get 530.83 times in minutes, so 531 or any reasonable rounding minutes. Make sure you write your minutes. No need to change that to hours and minutes. Minutes should be fine.
SQA Higher Maths 2024 Paper 2 Question 11. The number of electric vehicles worldwide can be modelled by n equals 6.8 e to the kt, where n is the estimated number of vehicles in millions. Watch out for that word. T is the number of years since the end of 2020, and k is a constant. Use the model to estimate the number of vehicles worldwide at the end of 2020. So at the end of 2020, t equals 0. So you get n equals 6.8 times e to the 0, which is 1. So that's 6.8, but it's not 6.8. 6.8 million. You'll probably lose a mark if you miss that word because it's not 6.8. Part B. At the end of 2030 is estimated at 125 million electric vehicles worldwide, determine the value of k. So we want n is 125 million, or 125 equals 6.8 e to the power of, and k, t. So t, 30, 20, 10 years, 10k. So that's a logarithmic equation. It's going to turn it, we're going to use logs because it's an exponential. So divide by 6.8. That equals e to the 10k. Take the natural log of both sides. ln, I'll write 1025 over 6.8 equals ln e to the 10k. 10k can come down to the front to get ln e, which is just 1, remember. And that is ln 125 over 6.8. And therefore, k is very simply ln 125 over 6.8
all divided by 10, which is a calculator job. ln 125 over 6.8, all divided by 10, 0.2911, blah, blah, blah. I think 291 is fine, 0.291, and that's K. Have we answered the question? Yes. So we're done there. Logarithmic graphs. SQA Higher Maths 2015, paper 1, question 13. The function f of x is 2 to the x plus 3 is defined on R, the set of real numbers. The graph of equation y equals f of x passes through 1b and cuts the y-axis at q as shown. What is the value of b? Well, it passes through 1b, so I can just sub 1 in. So for part A, we've got f of x is equal to 2 to the x plus 3. So at x equal to 1, we're going to say that f of x equals 2 to the power of 1 plus 3, which is 2 plus 3, which is 5. So just to answer the question, b equals 5. And we're done there. So part B says copy the diagram above, inspect the inverse function, and then write down the coordinates of the images of P and Q. What it means by the images of P and Q is what does P and Q become in the inverse function. So this is an exponential, so the inverse function is a log, so we need to reflect that in the line y equals x. So let's just go ahead and do that. So I've copied the diagram below. So we already know that P is 1b, which we've just worked out is 1, 5. And then let's work out our y-intercept for this graph. So that is when x equals 0. So f of x, which was 2 to the power of x plus 3. That's 2 to the power of 0 plus 3. 1 plus 3 is 4. So we get 0, 4. We need to reflect in the line y equals x. So drawing a y equals x sign. So 0, 4 becomes a long 4, 0. And 1, 5 becomes 5, 1. And we've got an exponential curve like so. That's the inverse function of x. So that's part 1 done. And then for part 2, I've already done the work for it. The image of P and Q, we've got 4, 0. And we've got 5, 1. And we're done there. Part C says, R3, 11 lies on the graph of equation y equals f of x. Find the coordinates of the image of R on the graph of equation y equals 4 minus f of x plus 1. So writing down f of x again, f of x, remember, was 2 to the power of x plus 3. And we know that the R lies on this, which is 3, 11. So our new equation is y equals 4 minus f of x plus 1. So what does that mean? Well, let's just take a few notes. In here means we move left by 1. Minus f of x means we reflect in the x-axis. And you can think of this, that's like plus 4, so move up by 4. If it helps, you can rewrite this as minus f of x plus 1, and then add the 4 in the end, and you might be able to see that better. So that means we've got our R, which was 311. So doing the things in the correct order, we apply our reflection, and then we move the left, and then we move up. So our reflection minus f of x plus 1, 311 becomes 3 minus 11, because it drops down underneath. And then that goes to moving left by 1, so 3 becomes 2, so 2 minus 11. And then finally, we need to move up by 4, so we get 2 minus 7 as our final answer. Now, if you're really struggling with that, one way to do it is to go back to the original graph and actually draw it, reflect it, move it to the left, move it up, and note that point moving around. Okay, logarithmic graphs, SQA Higher Maths 2016, paper 1, question 10. Diagram below shows the graph of a function log 4x, base 4. The inverse function exists. On the diagram, on your answer book, sketch the graph of the inverse function. Okay, I'll just draw you a quick sketch of this. So you've got your y-axis, you've got your x-axis, and you should know that a log graph's inverse is the exponential. It reflects in the line y equals x. So these points, you can just switch the order. So 1, 0 becomes 0, 1, and 4, 1 becomes 1, 4. So I can note 0, 1 on the y-axis, and it was 4, 1, so a long 1 up 4. Let's just draw it there. And there's our 2 points, and then all you need to do is draw your curve. And you can note that that is f of inverse f of x, f of minus 1x. And we're done there. Solving logarithmic equations, SQA Higher Maths 2018, paper 1, question 11. Diagram shows log 3x. On the diagram in the answer book, sketch the curve of equation 1 minus log 3x, and then find the point of intersection between the curves, which will be solved with logarithmic equations. So 1 minus log 3x, the minus part here tells me to reflect in the x-axis, and then the 1 part, which I'll do in another colour here, tells me to then move up by 1. So first of all, reflecting in the x-axis, this point will stay where it is, but this point will jump down here, and that would be at the moment as in point 3 minus 1. But now I have to move up by 1, so this point is going to jump up by 1, so that becomes 1, 1. And you can see this point goes up to 3, 0. So I can just write the number 3 here. Getting rid of my intermediate working, which you could use a rubber if you were doing this by hand. And since it's reflected, it's going to go down and through here. So we can just draw that in, down here, through the way, and there we go. It's a reflection in the x-axis. Okay, part B, determine the exact value of the point of intersection, simultaneous equations. So for part B, we've got y equals log 3x, but we've also got y equals 1 minus log 3x. So we can say that they are equal to each other and find x. So log 3x equals 1 minus log 3x. So taking the log 3x to the other side, you'll have log 3x plus log 3x, so 2 of them, 2 log 3x equals 1. I can take the 2 up as a power, so I get log 3x squared equals 1. Now I've got it in the form log of something equals a number, so 3 to the power of 1 equals x squared. 3 to the power of 1 equals x squared, and therefore I can find x. X equals 3 to the power of a half, or x equals the square root of 3. And we're done there. Notice it'll only be the positive part of this instead of the negative part, because if x was negative, then you'd have log of a negative number, which doesn't exist, so it's just a positive. I can take a note of that. Just positive value, as x has to be greater than 0.
SQA Higher Maths 2023, paper 1, question 9. The diagram shows the graph of function f of x is log base 3x. X is greater than 0, of course. The inverse function does exist. In the diagram in your answer book, draw the graph of the inverse function minus 1. Well, let's examine the inverse function first. The inverse function of a log is an exponential. And essentially, the easiest way to draw it, imagine a dotted line here, y equals x. The coordinates just switch places, okay? So here is my normal y equals x. So 1, 0 becomes 0, 1. And 3, 1 becomes 1, 3. And it just gives you an exponential curve. And that would be 1, 3. So that's the inverse function of x. So now I just need to take away 1, which means just to move it down by 1. So 1 is going to go to 0. And 1, 3 is going to go to 1, 2. So I can just draw it now. There's 0. It's obviously going to drop below because that's where your asymptote is, essentially. So it's going to go along, up through 0, and start climbing. Then we just put that point on that we noted, which was 1, 3, so it now becomes still 1, but 2, and we're done there.
Logs. Finding the relationship from a straight line. So in other words, changing the axis so that one or both become logarithmic axes, and then that makes a straight line, so we can work from there. So let's have a look at this question. Two variables x and y are connected by the equation y equals k times x to the power of n. The graph of log 2y by log 2x is shown. Find the values of k and n. So you can memorize how to do this, but I usually just start from the beginning, which is to say that y equals kx to the n. If I've got y equals kx to the n, I can log both sides. And the base is 2, so I can say that log base 2 of y equals log base 2 of kx to the n. Separating the product k and x to the n, I can say that log 2y equals, I'll write the x one first, log 2x to the n plus log 2k. So I can then write log 2y equals n comes down, log 2x plus log 2k. And that looks like now y equals mx plus c. That's like your big Y equals, that's like your mx plus c. So our gradient is equal to our n, and our c is equal to our log 2k. So if we can find the gradient, we know our n, and we can find c with where it cuts the y-axis, we know log 2k. So let's look at our graph. So for our gradient, we've got along 12 and up 3 over 12. So our gradient is 3/12. So our gradient is equal to 3 over 12, which simplifies to 1/4, and therefore n equals 1/4. Now to get our c, we know that log 2k is where it cuts the y-axis. Our graph tells us it cuts the y-axis at the number 3. So we're just solving log 2k equals 3. That means 2 to the power of 3 equals k. 2 to the power of 3 equals k. And therefore k equals 8, because 2 cubed is 8. And we're done there. Relation from a straight line for logarithmic graphs. SQA Higher Maths 2019, paper 2, question 12. Two variables x and y are connected by the equation, and this is what you're looking for. Y equals ab to the x, a power. And we're looking at one of the axes is logged, but the other one is not. So it's only one log this time. But always start from your equation and get the logs coming out and see where you go. So I'll start with y equals ab to the x. We'll have to find the values of a and b. So let's start with y equals ab to the x. Just log both sides then. Our log base is 4. So looking on our graph, log base 4y equals log base 4 of ab to the x, which is a product. So I can separate that into a plus. So log base 4y equals log base 4 of b to the x. I'll write the x one first, like mx plus c, plus log base 4a. Taking the x to the front, we get log base 4y. That's a y and that's a log. Equals x times log base 4b plus log base 4a. Well, y equals mx plus c is our straight line, so let's put the x on the end so you can really see it. Log base 4y equals log base 4b times x plus log base 4a. So that's like y equals mx plus c. So we can see our gradient is equal to this number in front of x, and our c is equal to this. So we can say our gradient is equal to log 4b. So let's just check our graph to see if we can work out the gradient. We're given 2 points. So our gradient is equal to y2 minus y1 over x2 minus x1. So that's 8 minus minus 1 over 3 minus 0. That's 9 over 3, which is 3. So we know our gradient's 3. So log base 4b equals 3. Remember, that means that 4 to the power of 3 equals b. 4 cubed is b. 4 cubed is 64, and therefore b equals 64. Now let's try our C. From the work we've just done, our C is equal to log base 4 of A. C is where it cuts the y-axis. We know it cuts the y-axis at 0, minus 1, so C is minus 1. So we can just straight away say that minus 1 is equal to log base 4 of A, or if you prefer, log base 4A equals minus 1. Remember, that means 4 to the power of minus 1 equals A. You can just write that straight away. 4 to the minus 1 equals A. 4 to the power of minus 1 is 1 over 4 to the power of 1. So therefore, A equals 1/4. And we're done there.
Question 7 says two variables x and y are connected by the equation y equals kx to the n. The graph of log 5y and log 5x is shown as a straight line. Calculate the values of k and n, and we're obviously given 2 points. So let's start this question. So we've got y equals kx to the n, and we've got the log base 5, so we can log both sides with base 5. So log base 5y equals log base 5kx to the n, which we can separate into two separates. Log base 5y equals log base 5x to the n plus log base 5k. Bringing the n down in front, we've got log 5y equals n log 5x plus log 5k. That's a bit like, because it's logarithmic, log base 5x and log base 5y, that's a bit like a big y equals mx plus c. So that's our gradient and that is our y-intercept. So we can work out our gradient because we're given 2 points in the question. Just remind ourselves 0, 3 and 2 minus 1. So our gradient equals minus 1 take away 3 over 2 take away 0. That's minus 4 over 2, which is minus 2. We can then do our y-intercept. That's c, remember. So c was log 5k. That crosses the y-axis at the number 3. So that means that 5 cubed equals k. So 125 equals k. So to answer our question, we had y equals kx to the power of n. So y is 125x to the minus 2, where k equals 125 and n equals minus 2. SQA Higher Maths 2024 Paper 2 Question 6. Two variables x and y are connected by the equation y equals ax b. The graph of log 5y and log 5x are shown and it's a straight line. So we've got log 5y by log 5x and find a and b. Right, so I always usually start with the equation. Some people skip ahead, but I don't like to. So I'll start with that and I log both sides. The base is 5. Log base 5y equals log base 5 ax to the b. So now I can separate my log out on the right hand side to log base 5a plus log base 5x to the b. So that means log base 5y equals log base 5a plus b comes out the front, log base 5x. And put that in a kind of form of y equals mx plus c. You've got your log base 5y. I'll take the x bit first. So b times log base 5x plus log base 5a. So now just comparing your graph, your y-axis is log base 5y, so that's like your y, and your x-axis is log base 5x, so that's like your x. So that bit there is your gradient, mx, and that bit there is your c. So the gradient is b. So what's the gradient of this line? Well, I've got 2 points, 0, minus 2, and 410. So the gradient between 0, minus 2 and 410 is what we're going to do. So my gradient equals 10 minus minus 2, 4 minus 0, that's 12 over 4, that's 3. So that means that to answer the question, b equals 3. Now it says find c. Well, I already know where it cuts the y-axis, 0, minus 2. So that's it. C is minus 2. So
if c is minus 2, that means that log 5a equals minus 2. So that means that 5 to the power of minus 2 equals a. That's 1 over 5 squared. 5 squared is 25, so a is 1/25. And we've got that, so we're done. This has been Clelland Maths today. We've done through the whole of logs in higher maths. All the logarithmic functions, all the exponential functions, log equations, exponential equations, graphs of related functions, experimental data. Take care, stay safe, and goodbye.